In the last several videos, we've been looking at a number of examples of how we can use diagonalization to solve systems of first-order ODEs. And in the last video, we extended that to higher-order ODEs as well. And you may be feeling a little bit like this poor guy here. So you can imagine what happened. Mom or dad here did something noteworthy, and they got invited to meet the president in the Oval Office. And they brought Junior along, told him, get a day off of school, get to go meet the president. They really set this up to be this awesome experience, and then he gets there and is like, man, I am so bored, and he does a face plant into the Oval Office couch. So I always love this picture, and it's maybe represents a little bit of how you're feeling right now. Doing a lot of examples, really getting into the details. And the reason for that is because this is such a useful and powerful tool in our mathematical toolbox for solving differential equations. What I like to do now is kind of pull it all together in a physical example. So this is an example from dynamics. It's a relatively simple spring mass system, but we're going to use it to kind of pull together some of these ideas that we've been discussing, using the methods we've been discussing as well, and show how they apply in a physical situation. So this is an example that's done using Hamilton's principle in variational methods, and here we'll use Newton's second law to get the governing equations, and then we'll solve it using diagonalization. There's not going to be any new mathematics in this example. We've seen all the mathematical machinery that we need to solve this, but it will be quite a bit more complicated example because of the physical nature of it. I've done nothing to try to hide some of the messiness of solving real problems. And in fact, I did not solve this problem by hand. I solved this using Mathematica. So you'll see that as we go through it. So here's the problem. We have two masses, the left mass of mass m and the right mass of mass 2m. And they're connected to the adjoining walls and each other by these three linear springs with spring constant 2k, k, and k. In order to specify whatever we would need to know about this system, all we need is the positions of the two masses, x1 and x2. If we knew those positions, of course we would know where the masses are. We could calculate the forces in the three springs, and we know the full state of the system. So we say it's a 2 degree of freedom system because there are these two dependent variables, which if we knew, we could fully specify the state of the system. And that's what degrees of freedom are. It's the minimum number of dependent variables required to specify or fix the state of a particular system. It also corresponds to the number of natural frequencies or natural modes of the system itself. So we would expect to find 2 natural frequencies, and we'll actually do that calculation in a little bit. Just one other further detail here. So these positions x1 and x2, when they're at 0, so at their 0 values, the spring mass system will say is in its neutral position. So there's no forces in any of the springs when x1 and x2 are 0. So let's go through the whole process. Let's start with applying F equals ma to our system. And that will give us the equations of motion of that system. Now remember, F equals ma, a is the acceleration, F are the forces. Acceleration is x double dot. It's the second derivative of the position vector. So the way we did this in a dynamics class, for example, would be to write down the free body diagram for each of the two masses. When you cut away something to form the free body diagram, you replace it with the forces that they apply to that body, that free body. So in this case, for the left mass, we'll call that 1. For the left mass, we have a force to the left from the left spring, 2k times x1, 2k being the spring constant for that linear spring, x1 being the elongation of the spring. To the right, this is the spring that's between the two masses. So the elongation is x2 minus x1, the difference between them, times the spring constant k. So mass times acceleration, x1 double dot, is equal to the sum of the forces, taking into account the appropriate signs. We can simplify those as we've done here. So we have mx1 double dot is equal to minus 3kx1 plus kx2. Then for the right mass, which is 2m, we do exactly the same thing. Pulling to the left is the same force as pulling to the right on the left mass. That's kx2 minus x1. And then to the right, we have minus kx2. Don't get bogged down in the signs. The signs work. They are correct. They apply in compression and tension, and everything's fine. So you can sort out the signs if you'd like, but for our purposes, it's somewhat of a distraction. So here we have the mass, 2m times x2 double dot, is equal to the sum of the forces, which again we simplify to kx1 minus 2kx2. So what we have in these two equations are two second order, because it's d squared dt squared, d squared dt squared, two second order ODEs that govern this spring mass system. 2 degrees of freedom, two second order ODEs, two dependent variables, x1 of t and x2 of t. We can express that in matrix form if we like, so I've given that here. We have a mass matrix, a damping matrix. There's no damping in this particular problem, a stiffness matrix which involves the k's. You have acceleration vector, velocity vector, displacement vectors, and all that. So you can put this into a general matrix form, which I'm not going to bother with for now. So in the next video, we'll actually solve this system of equations using diagonalization. It is a system of two second order equations, so they're higher order. We'll have to convert them to first order, and we'll do that in the next video. We'll solve it through diagonalization, get the solutions, and look how it behaves. But for now, I want to address this question that we've talked about a number of times as an application, and that is determining natural frequencies. They're inherent to the system itself, whether mechanical, electrical, biological, or chemical. And each of these systems has these natural frequencies. We expect there to be 2 for this system because that's the number of degrees of freedom. This is how we determine them. So a natural frequency, or a normal mode of vibration of a system, is one for which the entire system vibrates at the same frequency. So in our case, that would mean that both masses are moving with the same frequency. They could be in phase, they could be out of phase. Doesn't matter, as long as they're moving with the same frequency. In general, that's not necessarily the case. You have masses of different masses, you have different spring constants, so they're not necessarily moving with the same frequencies, but the natural frequencies are those situations where that is the case. So in order to calculate those, let's hardwire our x1 and x2 solutions such that they have the same frequencies. So the e to the I omega t is the same, omega being those natural frequencies. The A1 and A2, those are the amplitudes of oscillation. We don't actually care about those, but they'll come along for the ride. You'll notice I'm going to use this exponential form instead of using sines or cosines, and that's just so we could apply this to a situation where we have first order derivatives. So we could have 0th order derivatives, first order, second order, and all the terms would have this e I omega t. If you use cosine or sine, then the even number derivatives would be the same, but the odd order derivatives would be different because of the sines and cosines flipping back and forth. So we're going to use this form here, and then we simply take then the real part of that to get the sine or the cosine. Real part for cosine, imaginary part for sine. All right, so again, those details aren't terribly important. The point is we're going to hardwire into our solution that it has some amplitude, I don't know what it is, and it has the same frequency in both. So both x1 and x2 are oscillating with the same frequency, omega. Okay, so we're going to substitute those solutions, x1 and x2, into our system of two second order ODEs. I need x1 double dot and x2 double dot. So I take two derivatives of each of these, and I get minus a1 omega squared e I omega t, and minus a2 omega squared e to the I omega t. When I substitute these into our two equations, the 237, 238 governing equations, equations of motion, every term is going to have this e to the I omega t factor in it. I can cancel all those out of both equations, and I end up with these two algebraic equations. So what's happened here is when I'm looking for these natural frequencies, I've hardwired in those natural frequencies, and by doing so, I convert my differential equations into algebraic equations. And this is what they look like. The m's are masses, the omegas are the natural frequencies, and the k's are the spring constants. Now it's not quite so obvious what this actually is, so let me rearrange things just a bit. Let me bring the k's from the right over to the left-hand side. So I'll have m omega squared over k. I'm going to call that some randomly selected Greek letter. Let's just randomly choose lambda. And so if I do that, I'm going to flip the sides here to make it even more obvious what's happening. I have 3a1 minus a2 is equal to lambda times a1, and minus a half a1 plus a2 is equal to lambda a2. So those are my two algebraic equations that result from this normal mode or natural frequency calculation from our system of differential equations. So now you can see what's happening, particularly if I put this into matrix form. So let's just write this now into matrix form. So I have a 2 by 2 coefficient matrix, 3 minus 1 minus a half 1. That's from these coefficients right here. That's times a1, a2. That's the amplitude vector. Again, I don't really care about that, but it's coming along for the ride. Is equal to lambda times, again, a1, a2. So now you can see even more clearly what we end up getting. It's an eigenproblem. So this is always the case. If the physical question is, what are the natural frequencies of vibration of a system? The mathematical answer is, what are the eigenvalues? And those eigenvalues are related to those natural frequencies. You can see it here. My randomly selected Greek letter, lambda, is m omega squared over k. So we determine the eigenvalues. If you know the mass of the mass and the spring constant of the springs, then we can calculate the values of omega that we get for those eigenvalues. Now the eigenvectors themselves are actually the amplitudes. So again, I don't really care about those, but physically the eigenvectors would be the amplitudes of those vibrations, a1 and a2. So if you do that, you take our 2 by 2 matrix, you get the eigenvalues, lambda 1, 2 minus root 6 over 2. Lambda 2 is 2 plus root 6 over 2. And here I'm just reminding us that lambda is equal to m omega squared over k. And I'm also taking notice of the fact that I get two of these. I get two values of lambda because it's a 2 by 2 system, and therefore I get two natural frequencies, which again physically makes sense because it's a 2 degree of freedom system. So if I flip that around, if I solve for omega 1 and solve for omega 2, I get this. I get omega 1 is 0.8805 times the square root of k over m, and omega 2 is 1.7958 times the square root of k over m. Once I know k, once I know m, then these are the values of the natural frequencies. We call the smallest one, we call that the fundamental mode. So what we have are those natural frequencies that are inherent to the system. And what we're going to see in the next video when we actually solve the system, we're going to see these same frequencies are then superimposed to get the general solution of the systems. For any set of initial conditions, the general motion of the system is always going to be a certain amount of omega 1 and a certain amount of omega 2, and it's just a matter of how much of each one, so the superposition of those two natural frequencies. We'll see that in the next video.